Having now listed all of the energy stores and the many ways in which energy can transfer from one store to another, it's important that we now move our understanding to a quantitative understanding. That is, we are going to need to be able to measure and quantify the amount of energy stored in one store that is potentially able to be transferred to another. Now, the thing that we need to talk about first is that we are talking about something known as an open system here. An open system. Later on, we will talk about a closed system. But what is a system? Well, a system is that we are talking about. The objects involved. The system of a collision involves one car crashing into another car. Both objects are a part of that system. We could choose to focus our attention just on those two cars within the system. But if those two cars collided because of a pedestrian crossing the road, there might be this factor that influences the outcome of what is happening within the system that is external to the system. If we don't include the pedestrian in this picture, then we may never know why the cars collided. Now, having something that influences the objects within a system, external to the system, this is what we call an open system. Or more specifically, any series of objects that can be acted upon by external forces. A series of objects that can be acted on by external forces. So what do these forces do? Well, these forces have the capacity to change the energy. If I provide a pushing force on a stationary trolley, I might then find that its kinetic energy increases. If I apply a force onto a system, I might find that the net energy in that system goes up or down, depending on the kind of force that I apply. More about that later. The key thing is that the amount of energy in an open system can go up and it can go down. Energy can be lost outside of the system, and energy from outside of the system can come in. So in these situations, we can have the value of the energy change. It can go up and it can go down. And the equations that I'm about to show you are universally true. They work both within the entirety of an open system, but they actually also work as a small part of a closed system, as we'll see later. So what are the equations that describe the amount of energy that is stored in an energy store? And we're going to use the example to start with of kinetic energy, gravitational potential energy, and elastic potential energy. We need to know the equation, but we need to have an understanding of what affects the amount of those energies, and we can do that by looking at what is in the equation. Now, this is where the notation becomes important. We said in the energy stores video that the symbol for kinetic energy was E subscript K. Now I'm going to use a different colour to show you what the units are underneath. Each one of these quantities can be measured, and that measurement would have to be given with the correct unit. I can't say that I walked 5, but I can say I walked 5 metres. Now, kinetic energy is measured in joules. But what things are important in calculating the amount of kinetic energy that we have. We're going to equate this to some other things that contribute. Quite obviously, one of the things that does contribute is the velocity of the moving object. If you move faster, then you have more kinetic energy. If you move slower, then you have less. So velocity is very important. So we put it in the equation just there. Now, velocity is measured in the units of meters per second. 1 meter per second is 1 meter every second. But it isn't just based on velocity. Scientists realised that it was actually related to the velocity squared. The velocity squared. And so we put a little tiny 2 at the top to represent that the velocity, just the velocity, has been squared. Now this means that if I was moving at, say, 6 meters per second, then the velocity squared would be 6 times 6, 36. And so I have to put that into the equation. Another thing that the kinetic energy depends upon is the mass. The mass is important in telling us how much energy is stored in a moving object. A planet moving through space carries so much more kinetic energy than a spacecraft that is much smaller in mass. So I have to put the mass in here. And the mass is measured in kilograms. Now it's nearly complete, but one last thing that scientists found was that there had to be some constant of proportionality. To make these numbers work, they had to add one more thing, and it was a half. As in the number 0.5. A half times mass times velocity squared, and that gives you kinetic energy. The next energy I want to talk about is gravitational potential energy, E subscript P. This, as you remember, is the energy stored in something that is placed high up, that can be unlocked as it falls back down. Of course, this is going to be dependent on your height, the height at which the object has been lifted, h, the vertical height. But it's also dependent on some other things. It's dependent on the mass of the object. Obviously, a huge boulder at the top of a mountain is going to have more stored energy than a golf ball. And so the mass for this also becomes very important. M has to be in there. And so we can put the units on so that we know what we're doing. Joules, height is in meters, mass is in kilograms, but there's something else. One more thing that affects the amount of energy stored up in something that is lifted high, and that is the strength of the gravity on the planet that you're doing this. You see, if I lifted a spacecraft to the top of a mountain on the moon, it would not have nearly so much energy as placed on the top of a same-sized mountain on the Earth, because Earth's gravity is stronger. Now we need to represent that in our equation, and we do that with the symbol lowercase g. And this has the units of newtons per kilogram. Now, we need to talk about G for a second, because G is a slippery fellow. G stands for the gravitational field strength. Gravitational field strength. On Earth, G is equal to 9.8 newtons per kilogram. On Mars, it is equal to about 3.4 newtons per kilogram. because Mars is a smaller planet, its gravity is not as strong. On the moon's gravity is very weak because the moon is about the same size as Australia, and it is about 1.6 newtons per kilogram. And there's one last thing that I want to just say before we finish talking about potential energy. Most of the time, you will be given the mass and the height, and you will have to remember that the strength of gravity is 9.8. But sometimes, instead of the mass, they will give you the weight. Now, that weight is a subject for another video, but just so that you can process questions like that at this point, let me give you the key equation that is going to unlock this for you. The key equation is the connection between weight and mass. Now, weight, the force of gravity acting down on your body, is equal to your mass multiplied by the strength of gravity, G. And so your weight is going to be 9.8 times your mass. So if I had a mass of 100 kilograms, then my weight would be 980 newtons. If I get the weight, I can put it straight into this formula, because on a side note, the potential energy in terms of weight would be given by the weight, which is equal to mass times the gravitational field strength times by the height. So remember, there is a second way of doing it. Look at what you're given. Are the numbers given to you in kilograms or in newtons? If they're given to you in kilograms, use this. If they're given to you in newtons, use that. Now there's one more energy store that the equation I should give you, and that is elastic potential energy. Elastic potential energy is E. Now, this is the type of energy stored up in a spring, or anything that is compressible that would resist that compression. And one of the most important things is that the more you compress it, the more it presses back. The more you stretch it, the more energy you've stored in it. You would probably know this. If you've had a party hat and you've looped around the back of your head and you pulled it out and let it go, it'll snap you in the face. If you pull it further or further, a common experience would have you know that it would hurt more. So how far you have stretched it beyond its original length, that is the extension. And I'm going to put it in my formula just here. And what's important to know about extension is it can be calculated by taking the original length and subtracting from the new length the original length. So it's new length minus the original length. So if I had a spring that was already 3 centimetres and I extended it so that its total length was now 9 centimetres, you can see that my extension would be equal to 9 minus 3 is equal to 6 centimetres. It is how far it is stretched beyond its original length. That is the extension. And that is what is important when we talk about elastic potential energy. And similar to the kinetic energy, scientists realised that it was not connected to the extension alone, but to the extension squared. So a square has to appear just here. The units joules, the units meters, meters squared in this case. But scientists realised there was something else that is important in the amount of energy that can be stored up in a spring. The stiffer the spring, the harder it is to extend it, and the more vicious it is when you let it go. And when it comes back together, more energy was stored in the stiffer spring. that had been stretched to the same extension. So scientists had to get a handle on the stiffness of the spring, and they record that as the spring constant K. The spring constant K. So K is the spring constant. The stiffer the spring, the higher the spring constant. And it sits there. It is the force per unit extension. So the spring constant is newtons per metre. And again, echoing what we said about kinetic energy, we found that a constant of proportionality was required and that was equal to a half. And there we have it. The equations for kinetic energy, gravitational potential energy, and elastic potential